Well, today we'll talk to you about tracing for hardware, driver, and binary reverse engineering in Linux. So, let's see if that works. Magic. So, here's how I will proceed. We'll first introduce you to performance and behavior analysis tools, especially in Linux, and focus on the distinction between both. I will then talk about my LinuxTraceToolkit, which is my tracer project with both a kernel tracer and a user space analysis tool for those traces. I will then talk about application of tracing for reverse engineering purpose. I will then proceed to a small demo, a few demos in fact, and well then I will conclude. So analysis, we can have some types of analysis that are available in software. Some are targeted toward performance analysis, while others are more like, well, you want to understand the behavior of a program. So, on the side of performance analysis tool, you got profiling tools like tprof, gprof, tprof, or well, just a time command, top, which is very, very widely used. nmon, oprofile, which is a kernel profiler. Well, those are based on sampling of the information, most of them. So they do not give detailed insight of what the program is doing, but mostly gives an idea of where the CPU time is taken. Well, other kind of tool that can be used for performance tuning are event-based performance monitoring tools like LTT, SystemTab, LKST, just to name a few that are used on the Linux platforms. On the side of behavioral analysis, so what's interesting here is to have the complete information about, well, the execution flow of the program. You want to know how it acted. So tracers are especially good for that, and well, this is the focus of my presentation. So on Linux, you got LTT, LKST, strace is maybe the most widely used, and you just want to know every interaction that one specific program had with the kernel. LTrace also to get all the library calls of the program. And also, well, the debuggers are pretty good at that, right? So for the tracers, let's define two simple concepts. Events. What's an event? So, well, I just want to make sure that everybody here has an idea of what is a tracer. So, we got events. What is an event? It's an information record that has a timestamp. So you just log information and log the time at which it happened. And a trace is just an event log with many of those events. It doesn't need to be the same file. It's just a set of files with events. So now, on the side of my own project, LinuxTraceToolkit is a kernel tracer from the start. And then I extended it to have user space tracing capabilities, so I can trace libraries and programs. And so it's all instrumentation based. That means that, what is very good is when you have the source code, because you can insert your own trace points, your own instrumentation. What is instrumentation? It's the act of modifying code to put a statement in it, to record information. So when you're debugging a program that you own and that you have the source code, you can just put a printf in it. But, well, you will see that it's much more efficient and fast to use a tracer instead of that. What are the key features of LinuxTraceToolkit? Oh, by the way, LTT-NG stands for LinuxTraceToolkit Next Generation, as one would have guessed, and LTTV is LinuxTraceToolkit Viewer. So the key features, on the viewer side, LTTV, it provides an integrated modular analysis of, well, so we can analyze the information coming from all the systems, so from multiple information sources. So you can get at the same time information from the kernel, from the libraries, from the programs themselves, and analyze them and view them in the same tool. So well, this is one of the particular point where this tool brings analysis further than what exists. So it focuses on that while having a very low impact on the system performance and behavior. For the viewer, it also provides a cool GUI and as well as a useful text output and a framework to develop plugins to do some more analysis on the information. So, well, the goal of this conference is reverse engineering, right? So, I thought about the question, how can it be applied in reverse engineering? So, well, you can get information from programs, libraries, drivers. Well, you can instrument the network stack if you want. And so you can extract information basically from the operating system. So let's start with program analysis. Well, basically you can be confronted to two cases. One is where you have all the source code of an application that you just want to understand. And well, this is most of the work I do. I do this while having the source code. So this is white box analysis. But you can also be interested into black box analysis. And well, so what does this tool provide you when you want to do black box analysis? So if you only get a binary, so by adding all the OS operating system interaction that the program does, you can know, just like with S-trace, you can know everything that this program has asked to the OS regarding file system, network operations, inter-process communication, memory management, everything that you want to look at. If it's not enough for you, you can still use kpros or the system type project, which focus on inserting breakpoints in binaries and to be able to execute supplementary code. So, well, there's no reason why you couldn't just put tracing statements at those breakpoints. Well, it's especially well suited for analysis of multi-threaded and multi-process programs. As we will see later in a short example, we can show the flow of the execution of multiple applications. For example, if you have Mozilla talking with the X server and you want to know how back and forth the control went, this type of tracer is perfect for that. And well, as a plus, it also eludes debugger detectors. So let's go for a live demo. What I want to show you is, well, starting from, wait a second, okay. Well, that's why I don't do live demos. Okay, let's go for a non-live demo. So I would want to show you anti-debugging techniques. Well, I had a little look at it because I see that it's one of the strengths of a kernel tracer towards all the other tools that exist. For example, if you got S-trace, you will see that there are techniques that a program can use to find out that it's running under S-trace and to behave in a different manner. So I just wanted to make a point that, well, it can be useful. So then I will do a little study of the virus and go for, well, see, I have a little fun with all the information we can extract from the behavior of programs. So, if we want to talk about anti-debugging in Linux, well, I just want to do a little explanation of how debugging works generally in Linux. So it uses the ptrace system call. It's used by GDB, S-trace, L-trace, etc. What it consists of is only, well, so you are GDB, you want to attach yourself to a running process, which may be your child. So it gives you the ability to modify its memory on the spot. and to intercept all signals that are sent to this process, and intercept all the system calls that are made by that process. So it's it's a very convenient framework to intercept everything that is done by a program or to a program. But let's see what can be done against that. Because, well, okay, let's put ourselves in the place of a program which is binary only, and it doesn't really want to be debugged, right? And so, one technique, I don't know if you can see, not so bad. So, from this article from Silvio Cesare, just having the program doing a ptrace on itself and asking, okay, I want to be traced. Well, if it fails, it's because it's already traced. So, well, it's a way to elude a lot of debuggers, trace, etc. But, well, we can see that from the kernel side. So let's, we might find some other ways to do that in a stealth manner. For this program, the only important line here is this assembly line, which is int3. So what I did, I just put a breakpoint in my program, and just before calling the breakpoint, I connect the sig trap, which is the signal generated by a breakpoint, to a handler. So if I run unattached to any debugger, I will just call my callback and then come back to my code. So it takes a certain amount of time, which I calculate by getting the cycle counter of the CPU. And I expect this time to be quite short. So, well, what I do is, if I'm attached to a debugger, this breakpoint will cause a signal that will be intercepted by the debugger. So it will take a huge amount of time before I come back. So if I just test that, it's okay, I know that I'm being debugged. So I put myself at the place of someone who wants to run this program in a debugger. So what I do, I just find the source code, the object, and I find the spot where I've got the int3. So I can basically just replace every int3 breakpoints I find in the object with an up 0x90 on x86. And so we'll say, well, it's easy to elude, right? But if I replace with not, run it, well, in fact, I can elude the system. But detecting, well, I just made another program which detects not replacement. It times the time it takes for not, and then verifies if, well, as you see, it's a never-ending race. So basically, it points out that there might be a need for a system that traces the information without having such a big impact on how the system behaves, so it cannot be detected. Another program for detecting is trace, which uses this time a kill on itself, and this time it's calling an unexisting system call. And so, well, it's always by expecting some duration of this operation that is longer when it's traced, right? Okay, in real life, in a wild world, what uses this kind of technique? Well, I did a small research on the internet and found that this particular virus uses anti-debugging techniques. It's called the virus Linux RSTB. So it infects Linux binaries. What it does, just to sum up, it infects the current directory in /bin, and it puts backdoor on the network interface. So, well, why not? Let's have a little fun with it. We'll see what we can get. So I made a small setup using an emulator, and I put my kernel tracer in it. Okay, so this is the first example of the view we can have on the application behavior. So what we see here is the virus. So we see the para.tmp, which is, well, kind of an execution of small temporary file. That's weird. And it was the original process which has been launched with the virus. And we see that it's bound for 3 other threads, right? And then, well, it will call a probe and kill her. Well, the only point is that this projector is not quite good, because we would see a whole lot of lines drawn here. Well, too bad. What we see here is red lines, dark red, so that's why we don't see them. And it shows that most of the time, those processes are waiting for either this user, etc. So I decided to poke around in this virus. So I took a trace while this virus was running for the first time. And what I got is, well, this, okay, let me just explain you a little bit those views. So this is the process column. We see each process name. And we see the execution flow through time. And the different colors, when it's blue, it's running on behalf of the kernel is running on behalf of the process. When it's green, it's the process itself, which is running its own code. And we can see this this other color, which is when a process is waiting for CPU. Well, a legend of all this information right here. And this other view here is the one I think is the most interesting when we talk about details. It's the detailed event list. Every event that has been recorded in the trace appears here and can be filtered with a filter. So here what I see is the virus Linux RSDB process is calling a ptrace. So yeah, it's the first anti-debugging technique that it uses. What was not in the advisory is, well, it opens /root, and it wasn't, well, it had not been found out by the virus people. So, well, we can extract all the information about how the system calls that this program does, without disturbing the system behavior enough so that it would be detected. So, well, I just wanted to make some fun, seeing how it modifies binary files. It opens bin cat, and then does a whole lot of reads and writes on the file. So we see here everything that it modifies. Okay, another example application of that. Part of password snooping on a machine. Well, I recently implemented a dumping of the first 32 bytes of every read and write system calls in the kernel. Well, it was pretty easy. But what I thought is, wait a minute, there might be a security concern with that. Well, in fact, it's not a surprise to anyone. If we are the kernel, we own the machine, we see everything that happens there, right? But, well, adding that in a trace that we can take as easily as start tracing, we do our things, stop tracing, and we view it, well, it's beginning to be, well, quite facilitated. So, well, if we take, for example, the SU and SSH programs, well, the passwords will clearly be in clear text in the system calls, especially the read and write system calls of those processes. Well, I just decided to run a trace on the SU program and see, well, if I could get my password. So, first of all, I allocated the SU process, which is here, and as well, a red line there. And from there, I selected the interesting information with the filter, specifying that I wanted event name read, event name write, only for process SU. And I got there. We got SU here with only the events that we require. And we see that SU writes password and gets the data admin keys, which is not my password, but this is what I typed in. So, well, so it was a second example of how, well, this kind of big brother information gathering tool on a system can be used to see everything that happens. So it's not just targeted to one process or one thread, like most detailed behavior analysis tools are. It's, well, we get the information of all the system at once. So, well, following the Skype presentation, I decided to trace Skype in Linux. Why not? So, well, what I've seen is, well, it doesn't use any peak trace detection techniques. In fact, I ran it in S-Trace and it gave the same kind of result. Some weird things. It opens like 1,000 sockets. It tries to figure out very well how what are the characteristics of the machine it runs on. It calls times, which gets the system time information, CPU time used in the kernel, in the process, and calls that in a loop about 10 times with the same instruction pointer, so it's really from a loop that it calls it. So there might be some security features there. And it used massively that you render. But well, so that's just a small example, but well, what I'm showing you is one tool to get some more information about how your system behaves. It won't find everything. I mean, well, the Skype presentation showed very clearly that most of the things happen in user space. And what I'm talking about here is a kernel tracer. So, well, we cannot get that type of information without going, well, either, well, we don't have the code, but maybe putting probes in the program, but then, well, you see that it's not the solution to everything. About kernel reverse engineering. So we can, one of the areas that would be interesting to investigate is to do system call fuzzing. Where this tracer would be interesting there is to gather information about standard system calls, working system calls, and then from there generate fuzzing by modifying some valid system call input. So, well, this little module could be quite easily done with all the framework that already exists. To reverse drivers, well, I have not worked especially at drivers reverses, but I have some ideas about how such a tracer can be used in that area. So, if you look for every undefined symbol of a kernel module, you see, well, each symbol that it will use from other modules that might be also binary only, that you don't have the source code from them, but it can also be from kernel functions that are exported. So by instrumenting those kernel functions, you can gather some information from the driver. Also, by using kprocks on the driver, you can put breakpoints at, for example, every function entry, and then trace that and start to get some sense of how this driver interacts with interrupts, which code path has been called before generating an interrupt response from the device. Those kind of things. On the side of hardware reverse engineering, well, as every interrupt in the kernel goes through a path that is, well, in Linux, speaking, that is available for instrumentation. We have information about every interrupt entry and exit. So we can know the duration of these interrupt enders. We know the frequency at which an interrupt arrives. We could also make that with polling the devices periodically and dump that in a trace. So doing memory periodically or when a IRQ is received. So you could get some sense of how this device would be interacting with the driver. So as a conclusion, I invite you to try this program because I think that you might understand pretty better how your operating system and libraries and program works together from a starting point. And well, also if you want, feel free to contribute to it. It's open source, distributed under the TPL license. On the side of analysis tools, you can create your own test and graphical plugins. And on the kernel side and user space applications and libraries, there is a huge space for new instrumentation there. So if you want to try that, you're welcome. The framework is created for adding new contributions. Do you have any questions?